All right, last lecture, which was just moments ago for many of us, we were talking about gas laws. We introduced gas laws, we introduced pressure, and we talked about two of our simple gas laws so far. We talked about Boyle's law, that's P1 V1 1, and Charles' law, V1 over T1 1. And as it turns out, we can combine those gas laws, and when we combine those gas laws, we call it the combined gas law. So Boyle's law, P1 V1 equals P2 V2, can be combined with Charles' law, V1 over T1 equals V2 over T2. And basically, you just overlap them, right? They just overlap. And that worked out surprisingly well. So it's P1 V1 over T1 on one side, and then the same thing but with two subscripts on the other side. And just like with our other gas laws, the temperature is in what units? Kelvin. That's right. So we want to make sure that our temperature is in kelvins. And this is our combined gas law. Okay, so we can do calculations with our combined gas law. With our Boyle's law, with our Charles' law, the ones that we were doing last lecture, it was very important that we get our variables all labeled. We've now got two extra variables. So it's +2 important that we label all of our variables. So let's read through and find all our variables. We got a sample of gas initially at a volume of 241 milliliters and at a pressure of 755 millimeters mercury and a temperature of 32 degrees Celsius. All of these are in the same sentence. They all go together. So our initial volume, our V1, 241 milliliters. Again, you could label this V2 if you're feeling spunky. It doesn't really matter just as long as they all get the same label. And our pressure, 755 mmHg. And our temperature, 32 degrees Celsius. Then the gas is compressed to a volume of 115 milliliters and heated to a temperature of 94 degrees Celsius. We want to know what's the final pressure in millimeters mercury mmHg. So this 115 milliliters and 94 degrees Celsius are our second volume and temperature. So V2, 115 milliliters, T2, 94 degrees Celsius. What should we do before we start rearranging, before we start plugging numbers in? Convert. We should convert what? Our temperature should get converted to Kelvin. So we add 273.15 Kelvin to each of these. And we get 305.15 Kelvin and 367.15 Kelvin. Okay, just double checking that my brain did that right. And then we need our combined gas law. So again, we're just overlapping the parts of Boyle's law and Charles' law that line up. So P1 V1 over T1 equals P2 V2 over T2. And we are looking for pressure. So we're going to solve for P2. Solving for P2, we need to move V2 and T2 so that P2 is all by itself. So we multiply by T2 and divide by V2 on both sides so that our V2s and our T2s cancel out on the right side and they're moved over to the left side. And then for convenience's sake, I'm going to switch them left and right so that P2 is on the left and we get T2 and V2, and all the rest of our variables. We have all 5 of those variables, so we can plug them in and see what we get. So our T2, 367.15 Kelvin, times our P1, 755 mmHg, our V1, 241 mLs, divided by our V2, 115 milliliters, and our T1, our T1, which is 305.15 Kelvin. Go through and check and make sure units cancel out. Kelvin on top, Kelvin on bottom, those cancel. We also have milliliters on top and bottom, so those cancel. And what's left over is millimeters of mercury on the top. The units canceling is just one way of checking that we didn't screw up the algebra. This won't always catch every way that we could screw up the algebra, but it's one way that we can check and make sure that our algebra isn't messed up. This also helps remind us what units we are getting from this calculation, because it's not always going to be the units that we're asked to provide. In this case it is, so we don't have another conversion to do. So then we throw all of those numbers into our calculator. So multiply everything on the top, divide everything on the bottom. And the pressure is 1,903.6 ... millimeters mercury. We'd round that for 3 significant figures. And so then it gets turned into scientific notation. Questions? I don't usually do too much combined gas law stuff because there's so many variables. So that'll do it for combined gas law. But there's still more simple gas laws. We're not even covering all of them. We've got one more that we're going to cover, Avogadro's law. We've heard Avogadro's name before. Where have we heard Avogadro's name before? It's related to moles in atoms or moles in molecules. He's got that number. This number, right? That's the number of atoms in a mole, where any particle equals 1 mole. So Avogadro, hopefully, we can associate with moles. Moles is in our Avogadro's law. So what if the amount of gas changes? Because we haven't been changing the amount of gas particles in any of our other simple gas laws. If you measure the volume of gas while varying the numbers of the moles in the sample, you can get some data that is what Amedeo Avogadro collected. And I don't have a slide that shows the data. But this is something that we have experience with, and there's a picture of that on the next slide. So the volume of a gas sample increases linearly with the number of moles in a sample. So volume increases when N, the number of moles, increases. If one goes up, the other goes up. If one goes down, the other goes down. But usually it's going to be moles that's driving that formula. We're going to be assuming constant temperature and pressure for this. And so here's our Avogadro's law. The volume of a gas and the amount of the gas in moles are directly proportional. So we've got our little is proportional sign, or little alpha, little fish sign. So we get V1 over N1 equals V2 over N2. And if you wanted to memorize the simple gas laws, this is the one that you'd memorize for Avogadro's law. So anytime you've got volume and moles, and then another volume or another moles, this is the law that we would be using. And the way that we've probably experienced this, hopefully most of us have experienced this, is blowing up a balloon. If you've blown up a balloon, or if you've been in the same room as somebody who's blown up a balloon, you have experienced Avogadro's law. So initially you start with a tiny little piece of rubber, you put it on your lips, you start blowing into it, and when you're blowing into it, you're adding air into the balloon. The more air that you blow in, the more moles of gas that you're putting in, the bigger the balloon gets, until eventually you either stop blowing in or it pops. So Avogadro's law is just explaining what happens when you blow up a balloon. That's kind of all we're doing with that. So let's do an example problem with Avogadro's law. So V1 over N1 equals V2 over N2. So we've got a balloon that's been filled to a volume of 1.90 liters with 0.0920 moles of helium gas. If 0.021 moles of additional helium is added while temperature and pressure are constant, what is the new volume of the balloon? So we've got a volume, which is 1.90 liters, and we've got two mole values. Moles get the symbol N, so 0.0920 moles He, and we have this other amount of moles that we were given. That's also helium. There's a trick in this question as well. But first, let's identify which of those two numbers of moles does our volume pair with. We've got 1.9 liters. Does it go with this first mole number or the second mole number? Which of those is it linked to? It goes with the first one. They show up right next to each other in the problem. 1.90 liters with 0.092 moles. So I'm giving those the label 1. You could give them the label 2. It doesn't matter, just as long as they stay together. Okay, what do we expect? So what are we doing to the balloon in this problem? What's being done to the balloon? How are we changing it? We're putting moles in. Okay, so we're putting moles in. If you put moles into a balloon, do you expect the balloon to get bigger or smaller? Okay, so balloon gets bigger is what we expect. And I'm pointing this out because this can help catch us in case we don't catch the trick, in quotation marks, of the problem. So if we just take the numbers that we were given and we plug them in, the thing that we don't have is V2. And we already made a prediction based on our experience with balloons. If you blow into a balloon, the balloon will get bigger. We're adding to the balloon, so the balloon should get bigger. We're solving for V2. So we multiply both sides by N2 to get V2 by itself. And V2 equals N2 V1 over N1. And if we plug in our numbers for this, you don't have to do this, you can just watch along. We've got moles of helium on the top and the bottom, so those cancel. Liters is the unit that's left over, but if we look at what happens with our volume, our new volume is predicted the way we've calculated this. Our new volume is 0.433 and some change liters. Is that bigger or smaller than our initial volume? That's smaller than our initial volume. So something must be wrong, right? Because we know that if you blow into a balloon, the balloon should get bigger. So what's the thing that we missed? In the problem, it says if this many moles of additional helium is added. So we're adding this helium on top of what we already had in there. And so we need to add our N2, what we've got here written for our N2, this 0.021 moles. We have to add that to our initial moles. So that's the trick that we were missing. Because this 0.0210 moles is additional moles. So we add that to our original amount of moles. We get 0.1130 moles helium is our actual N2 value. So now if we solve for V2, 0.1130 moles helium times our initial volume, 1.90 liters, divided by our initial number of moles. The moles of helium still cancel out, but we should now get a bigger number than our initial volume, which is what we expect. So our new volume is 2.33 liters, which is bigger than our original volume, so this fits with what we would expect. It's a slightly less straightforward simple gas law problem, so I usually put maybe 1 on an exam. Questions about solving that problem? I would like to point out that the way that I have my exams written, this wrong answer will be one of the options. If I put this on an exam, this would be one of the options. Okay. Another one. This one's for you to try. We've got a reaction vessel with a movable piston. We're going to be using Avogadro's law. How did I write it before? V1 over N1 equals V2 over N2. So I'll give you some time to work on that one. Feel free to chat with your neighbor. All right, let's go through and label the things that we know. So we've got a reaction vessel. We've got a container. It's got a movable piston, so the volume can change. We fill it with some moles of one reactant and a different number of moles of a different reactant. Our initial volume of the vessel is 1.53 liters. I'm guessing that we'll probably call that V1. So that's 1.53 liters. After the reaction is complete, so at the end, the volume is 0.884 liters. So we'll probably call that V2, 0.884 liters. And what are we asked to find? Moles. It says how many, and then moles. How many moles are present in the reaction vessel? This is at the end. So we don't have N2. And we were also given some numbers of moles at the start. Moles of A and moles of B. Which of those are we going to use as our N1? How many moles do we have to start? Me doing hand motions, putting my hands together. We combine those two numbers of moles. So our total number of moles at the start is, if we add the reactant A, reactant B together, that's the total number of moles. So that's the trick, if you will, with this one. So 0.121 moles plus 0.452 moles. So our initial number of moles, 0.121 plus 0.452, 0.573 moles. Okay, so if you were stuck on that part, understandable. Hopefully we're past the sticking point. Rearrange and solve. All right, so we are looking for N2. N2 is down here. It's in the denominator. It's on the bottom side, on the right side. So there's a couple of ways that we could screw up when we're rearranging this. One of the ways that I've seen people screw up rearranging this is we know that we have to get rid of the V2, right? We need to move the V2, and so we divide both sides by V2. And then magic happens, and you rewrite this. Notice where our N2 is. It's still on the bottom, right? Sometimes people will magically rewrite this as N2, and then the other side is V1 over V2 N1. What mistake did I make when I did this? N2 was down here, and I magically flipped it to the top. And we can't do that. We would also be able to catch this mistake if we put in our numbers. So if our volumes are in the same units, the volume units will cancel out, and our N1 units will be left on the bottom, and that could be assigned to us, hey, we screwed something up. So that's one way that I see, one common way that this sort of problem gets messed up. There's a way that I think is easier to fix or to rearrange this equation, right? So if we've got N2 on the bottom, that's kind of inconvenient. To get N2 to the top, we have to move N2 up to the top on the left side. We have to move this whole left side over to the right side. It's a whole lot of algebra. What we can do to make the process faster is we can flip the top and the bottom on both sides. This costs us no money. It's absolutely free, and it hopefully doesn't cost us very much brain power either. So we flip the top and the bottom. So now the left side is N1 over V1, and the right side is N2 over V2. And now N2 is up on top, and so if we get rid of the V2, N2's on top of the numerator. It's where we want it to be, and we won't have made a mistake. So times V2 to both sides. The V2's cancel, and so N2 is equal to N1. That looks kind of like an H. Anyway, V2 over V1. Do we have algebra questions? You can also do it the long way. As long as you arrive at N1 V2 over V1, everything will be okay. All right, since we already have our volumes, we figured out the one little trick. Chemistry instructors love this one little trick. We can plug in our numbers. So our N1 is 0.573 moles. Our V2, 0.884 moles, liters. And then 1.53 liters on the bottom. We've got liters on top and bottom, so those cancel. And the units that are left over are moles, and importantly, the moles are on top. They're not underneath. So we get 0.331, after rounding for 3 sig figs, moles of whatever our product is, plus any maybe leftover reactant. Questions? Okay, this concludes the simple gas laws. We're done with simple gas laws. We're learning now the ideal gas laws. So as it turns out, all of the simple gas laws, the ones that we've seen and ones that we haven't seen, you can combine them all into a single law that rules them and in the darkness binds them, whatever. Lord of the Rings reference. So our ideal gas law, this is one that you should memorize. Please memorize this. Put this into your brain. Write it down. Get it tattooed. Don't get it tattooed. But if you did, that would be cool. But you won't get extra credit for it. PV equals nRT, the ideal gas law. So in PV equals nRT, P, V, N, and T are all things that we've seen before. We saw them in our simple gas laws. R is new. R is the ideal gas constant. The ideal gas constant has so many units. It has so many units. This will be given to you on the exam, by the way. So don't memorize that one necessarily. Okay, so R, one value of it is 0.0821 liters times atmospheres over moles times Kelvin. And this shows up, there's this version, it's on your yellow sheet if you have your yellow sheet handout still. There's also one that's got slightly different units. You can find like 15 other versions of R that have all sorts of weird unit combinations, but this is the one that we're typically going to use. One thing that's really nice about R value, it's not nice that it has so many units, but it is nice because it tells us what units everything else needs to be in. So our other quantities have to be in the same units that R has. So our pressure needs to be in atmospheres. Our volume needs to be in liters. Our amount of gas needs to be in moles. It's pretty much always going to be in moles anyway. And our temperature needs to be in Kelvin. So this is another reminder that our temperature has to be in units of Kelvin. So we can potentially catch ourselves if we're writing our units out and canceling them out like we should. We can catch ourselves if we accidentally put in degrees Celsius or if we accidentally put in millimeters mercury or torr or some other units. So that's kind of nice. Not nice because it's a lot of units to write out. It's annoying for me, so I understand it being annoying for you, but we do it. Okay, so that's our ideal gas law. And I had mentioned last lecture, we can make our simple gas laws from this, our ideal gas law. So we can take our ideal gas law and make the simple gas laws. So if you don't want to memorize your simple gas laws, you can start with your ideal gas law, PV equals nRT. If we have a problem where P and T are changing, those are the two variables that are changing. We haven't seen a simple gas law for this. So what we're going to do is we're going to put P and T onto the same side. And I screwed up when I was making this slide, so that should be V. So we rearrange. We move the V over, we move the T over, we get P over T equals NR over V. And we say, let's assume that N, R, and V are constant. So N, R, and V, nothing's going to change with them. So we copy paste P over T on the other side, and we get P1 over T1 equals P2 over T2, which is one of the other simple gas laws, Gay-Lussac's law. It also works for all of our other simple gas laws. Works for all simple gas laws. So if you don't want to do all that work of memorizing them, you can come up with them this way. And I usually don't have you like memorize the formula related to the name because the formula is more important than who it's named after. It might come up maybe one question tops, like what two things are related in Boyle's law or what two things are changing in Boyle's law. If you have questions about how to do this for the simple gas laws to come up with them for the simple gas laws, our SI Logan would be happy to show you during his SI session from 3:30 to 5:30. So one of the things that's cool about our ideal gas law, which is PV equals nRT, is we only need one set of variables. We don't need two states. We don't need an initial pressure and a final pressure. We just need one pressure, and we can figure out whatever our missing variable is. So we've got this question: what is the volume? Volume's right next to our question words, what is? So we're finding volume. What is the volume of 0.453 moles of gas? So N equals 0.453 moles at a temperature of 473 Kelvin. So T equals 473 Kelvin. and a pressure of 2.7 atmospheres. So P equals 2.7 atmospheres. We would go to our information sheet of our exam. We would look at our yellow sheet. We would refer to the slides. We would type on google.com, what is our ideal gas constant? And we'd find R equals 0.0821 liters times atmospheres over moles Kelvin. And we write down all of the units. I'm writing down all the units to show you that we can do it, even if it's annoying. It's helpful. I think least of all people, maybe second least of all people, because we've got a guest today, don't need to write down the units to do the calculation correctly. It's helpful to make sure that we are doing the calculations correctly. So I encourage you, please write down the units every single time, even if it's annoying. Okay, now getting on to solving the problem. V equals, who knows? So we need V by itself. We're solving for V. So let's move P. So we move P from the left side to the right side, and we get V equals nRT over P. Always a good idea when we're doing ideal gas law problems, go ahead and check, make sure our units are matching. So look at our R value units. Do we have liters? Liters would go with volume. Do we have atmospheres? We have atmospheres. Do we have moles? We have moles. Do we have Kelvin? We have Kelvin. So our units match up. We don't have any conversions to do. This is the sort of ideal gas law problem that we like. So we write in our values, 0.453 moles. We write in our R value, 0.0821 liters, atmospheres per mole Kelvin. We write in our temperature value, 473 Kelvin, and we're dividing by pressure, 2.7 atmospheres. And then if we're not sure about the algebra, we might be able to, maybe, catch ourselves if we screwed up the algebra by checking off, making sure all our units cancel. So we've got moles up here, we got moles on the bottom of our R value units. We've got Kelvin up top. Kelvin's in the bottom of our R value units, so those cancel too. Atmospheres down here cancels with atmospheres way up there. And the units that are left over are liters. And then it's a calculator drill. So multiply everything on the top, divide everything on the bottom, and then we round to 6.5 because our atmospheres only has 2 sig figs. So 6.5 liters. Questions? If the algebra is confusing you, Logan's also a great place to go for help with rearranging equations and doing algebra. You could also come to my office hours in the mornings, 8:45 to 10. Okay, you've seen it once. It's your time to shine. So PV equals nRT, R equals 0.0821 latum per molk, liters atmospheres per mole Kelvin. Give you a little bit of time to work on this one. All right, I'm going to write in our variables over on this side. Just so that we've got them. And we're looking for pressure. Okay, so to solve the problem, we're looking for pressure. That's P. So we want P by itself. So PV equals nRT, our ideal gas law. We divide both sides by V. This moves V from the left side to the right side. So we're left with P equals nRT over V. We can check our units. We've got liters. We've got liters in our R value, moles, moles in our R value, K, K in our R value. So all our units look like they'll match up. We can plug and chug, as they say. So 0.55 moles times the weight of all the units that you could possibly imagine, times 306 Kelvin, divided by our pressure, our volume, 8.5 liters. We go through on a spree, crossing things off. And atmospheres are left over. Plug everything into our calculator. And we round to 1.6 atmospheres. 1.6 atmospheres is the pressure in our tire. For those of you that are somewhat familiar with PSI, this is about 24 PSI. So if it's a car tire, probably a little on the low side, depending on the tires that you've got on your vehicle. For those of you that are especially mathematically inclined, for those of you that are really good at algebra, you can also use the R value units. If you know which of these units you're looking for, you can use R either on the top or the bottom to get whatever unit you want on the top. Cancel everything else out in case you forget PV equals nRT because you didn't get it tattooed on your forearm. Like I recommend you don't. Don't do it. Okay, so those were nice ideal gas law problems. Ideal gas law problems will not always be so nice. So we might get something like this. This is the ideal gas law, but something that's changed is that we now have to do unit conversions. So what volume, nice that volume's right up front next to our question word. Volume equals, who knows? What volume is occupied by 3.76 grams of oxygen gas at a pressure of 88.4 kilopascals? Look, it did show up. And a temperature of 19 degrees Celsius. Assume the oxygen is ideal oxygen. That sounds like I distribute oxygen, but I meant that the oxygen is ideal. Okay. Our R value, as a reminder, units of liters times atmospheres per mole Kelvin. So we've got a pressure we were given, pressure 88.4 kPa, kilopascals. Our temperature is 19 degrees Celsius. What do we need to convert those to? What do we need to convert kilopascals to? We need to convert it to atmospheres. So we would have to look up on our table of pressure units how many kilopascals or how many pascals are in an atmosphere. Turns out that for every 1 atmosphere, it's 101.325 kilopascals. So we divide by 101.325, and we get 0.8724 because there's some other stuff back there, atmospheres. What do we need to convert our temperature? To Kelvin. So for Kelvin, adding our 273.15 Kelvin. And we get 292.1 Kelvin. What other variable do we need? So if we look at PV equals nRT, we're finding V. Okay, so I'll give this make that fuchsia. We were given pressure, we were given temperature, and R is a constant. So the thing that we're missing to solve this problem is N. What's N? N is moles. Do we have something that we can convert to moles in our problem? We have grams of oxygen gas. So we can use this mass of oxygen gas and convert to moles. What's the formula for oxygen gas? It's O2. How do we know it's O2 and not just O? We know it's diatomic. We had a couple of mnemonic devices, right? So we remember our H7, hydrogen, and then this 7-looking shape from nitrogen to fluorine down to iodine. Oxygen's in there. We also had Brinkelhoff, O being the O in Hoff, Brinkelhoff. We also had horses need oats for clear brown eyes. So O is the oats part. So this is going to be O2. And since it's O2, we're dividing by 2 times the molar mass of oxygen gas, grams, and then moles flips to the top. Cancel the wrong thing out. Okay, so 3.76 divided by 31.998. 0.1175 ... moles O2. That's the trickiest part of the problem. The rest is the same as the other ideal gas stuff that we've been solving for. So divide both sides by P. V equals nRT over P. This is where it's especially helpful to use that ... because it saves us writing out even more stuff. Any questions while I'm writing out all these units? Okay, and then our atmospheres cancel, our liters don't cancel, but our kelvins cancel, and our moles cancel. And our volume is 3.23 liters. Questions at all? Okay. Other stuff that we can do with the ideal gas law, we can also find the molar mass of a gas. We will also need, in addition to the ideal gas law, we are going to need a mass measurement. We'll need the mass of the gas. So for example, a sample of gas has a mass of 38.8 milligrams, a volume of 224 milliliters, a temperature of 55 Celsius, and a pressure of 886 torr. We want to find the molar mass of the gas. Now in hindsight, I should have made these all in very convenient units, so it's less work for me to do when I'm showing you, but hindsight is 50-50, isn't it? So our ideal gas law, PV equals nRT R 0.0821 liters atmospheres per mole Kelvin. We would have looked up the R value if we didn't memorize it from doing the homework questions, and we would have had memorized PV equals nRT because it's just that important. And then we can write down our variables. Volume is 224 milliliters. That's the same as 0.224 liters. Divide by 1,000, milli equals 10 to the minus 3. For a temperature, 55 degrees Celsius, we're going to add 273.15, turn that into Kelvin. We get 328.15 Kelvin. Our pressure is 886 torr. Torr are the same as millimeters mercury. See, I told you I would do it. And there are 760 of those in 1 atmosphere. So divided by 760 torr, 1 atmosphere on the top. We could look that up on a table. I'll give you the pressure units. I don't expect you to have all of them memorized, but this would be a good one to have memorized. So divide by 760, and our new pressure, 1.165 ... atmospheres. Our goal is to find the molar mass of the gas. What are the units of molar mass? It is usually, the way we see it, grams per mole. So if we want to calculate the molar mass, we need an amount of grams and we need an amount of moles. We were given a mass in milligrams. We can convert that to grams. We do not have moles. So what we're searching for, what we're looking for with this problem, with this PV equals nRT, is we're looking for moles, the N here. So we have to move our RT. So our retweet cancels on the right side, moves to the left side. We've got N equals PV over RT. And we've got P, V, R, and T. We even have them in the correct units because we did the conversions already. So now we plug in our numbers. 1.16 and change atmospheres times our volume 0.224 liters over our value liters, atmospheres, moles, Kelvin, and 328.15 Kelvin on the bottom. And then we get to cancel everything out. Most things out. Our atmospheres cancel, our liters cancel. The moles and the Kelvin that are down here are secretly, because of the way that division works, they're secretly on the top. So this Kelvin cancels with the Kelvin, and this moles, because it's an inverse of an inverse, it's divided by, flips to the top. It's the division version of a double negative. So this will give us an amount of moles. And it's once again calculator time. We get 0.009, need more room, 692 ... with 3 sig figs moles. And this is what we're going to plug in to this grams over moles. So the 38.8 milligrams up here, I'm going to convert in place 0.0388 grams. So 0.0388 grams over 0.009692 ... moles. Our units, because nothing canceled out, are grams over moles. And we get a value of 4.00 grams per mole for the molar mass of our gas. Questions? Confusions? Contusions? So that was fun, but what's more fun is what gas is it? Any guesses what gas that could be? With a molar mass of 4.00? It's helium. And that's just like a fun little bonus thing that we can do. So if there's no questions, then we'll stop there for today, and we'll pick up on this slide next class.